Okay, I guess we should start because we are 3 minutes ahead of the schedule. So I would say cześć. Cześć. Thank you so much for being in my session. So I have actually two big challenges. The first challenge is that you are after lunch, so you may be more sleepy. The second challenge is that I'm reading this session after the session of Dr. Venkat Subramanian. So it's even more challenging for me right now. So just a few words about me. My name is Dmitry Aleksandrov. I work for T-Systems. And I'm a Bulgarian Java user co-lead. And as you see from here, I like airplanes. Yes, I even could program this one, A320. But I'm mostly, involved in coding in Java and mostly for Bloody Enterprise. And I also try to do conferences. Okay, so we have a plan for today. We want to rethink the way that we use system resources. And I truly hope that after this session, you will at least try to, at some situation, you will trigger the event on how would you do this or this or another stuff. So, and to do this, we actually need to understand one word, which is the word asynchronous. So what did I get from Wikipedia? What is asynchronous? So asynchronous is a form of a computer control timing protocol in which a specific operation begins after receiving a signal. And actually the operations are going not the same rate or not exactly the same rate together with something else. And in simple words, what do we actually do? So I start task somewhere else. We are not defined this else, but somewhere else, somewhere in the background. And after this task is ready, actually, we want to be notified that we have the result. And I need then after to somehow take this result and process it. In terms of Java or maybe other languages, so what we usually do, we start a new thread, put some work inside there, do something there, and then try to think how should we get out this result from there and somehow to process it. So there's a big headache on how to get this result, how to get it synchronously, and so on and so on. And why on earth should we actually do asynchronous stuff? Yes, because it can be really faster. Yes, it can be faster. Because why? Because it's a non-blocking approach. Because there are no gaps between tasks. Right after the task is ready, we start with another task. And as it's non-blocking, we are actually benefiting from that. Because blocking is waiting. It's doing nothing. And as we do nothing, all other resources are just wasted. And we want to avoid it at maximum possibility as it is. So, and to get this understanding on how can we do this in Java 8 mainly, we need to have a look at it from some different perspectives actually, because several technologies made it possible. We actually evolved to this position, so now we can use it quite easily. So, let us make some, step back to history and see the evolution of multithreading. So, all of us, mainly in universities, I guess, somebody from you from schools, we have begun to offload some work as we start new threads. So it was kind of a very, straightforward. We implement runnable, so do some work define some work to be done in run method, then we just start new thread. Or we even can extend the thread and do some work there. But at a certain point, we realize that, parallel programming is very hard. It's not just floating a work somewhere there and taking it back. And it's very hard. So all this waiting, yielding, synchronizing, and so on, it's very hard. How many of you have read this book? How many of you have read it once and understood everything? Okay, how many of you have read it 10 times and understood at least 10%? That's me. I read it every year, and every year I find something new. Yes, because it's very, very hard. But still, this book is amazing, and it's a must-read book for everybody. So, and at a certain point in 2004, people somehow realized that this concurrency stuff is very hard, and we have to make it a little bit, easier. And in 2004, there was released this concurrent API with the Java 5, and there were several constructions which were available to people, to the users, which somehow put off this low-level abstractions to something higher level, and at least they thought it will be more understandable. It's still not very much understandable, but still they have introduced this thread pools, or we could now offload this work and somehow say execute this work, do this asynchronous stuff, and so on and so on. Still, it was, kind of a little bit, high level of abstraction. And with it came the future. Yes. So what is a future, actually? By the terms of, theory, this is a primitive for creating multithreaded applications. And you will be surprised, this is something not very much new. The first concept of future was introduced in 1977. I wasn't even planned to be born at this time. By this wonderful paper of Henry Beck and Carl Hewitt. Actually, it was about garbage collection. It was fun. And what is actually a future? So if you know every function, so every work in our computers are made to calculate something, to do some work for us. And a function, something produces a result. So, and as this function produces a result, we have a function, we want to put this work, or actually the production of this result, in some kind of a container, because containers are now everywhere. We cannot start a conference if there is no word about containers. But container is not theoretically defined word. We use it just for our abstraction. So we put this work, the result of production of this work, inside of a container when we actually handle it and care for it. So, and putting this work in a container, you will be surprised. There is another word which always comes together in our in words in future, is actually the promise. So promise is actually the calculating of this work asynchronously and putting it inside a container. So container, we can consider it as a write once container, where promise puts a work. So this write once container is called future. So they always come together. They are sometimes mislead that future is a promise and promise is a future. Actually not. They are different parts of the same. So, and you will be surprised that this is actually not very much new stuff too, because the term promise was proposed even earlier in 1976 by Daniel Friedman, David Weiss, and Peter Halbert called it eventual. Just, try to understand, try to feel the word eventual. So we have this core word of event here. So this is a wonderful paper. I could even buy it on eBay or something like this. It's not public, but it's very interesting to read. So, and as we talk about, work inside of a container and so on, the main concept of future is that all the magic, all the work should happen inside of this container without ever leaving it. So we put a work, we put a function there. It produces some kind of result. We can transform this result in a container. We can chain this transformation of the result. But and then at the end, as we actually produce whatever we want, we are eligible to take this value out of it. We cannot just, take the value, put it inside of a container, do something asynchronous, then pull it out. do something asynchronous and put it back. So we actually, by the concept, we should never actually remove the value outside of a container. And as the expected, calculation, expected result is done, we actually do callbacks to pull it off and use it. So it's a final terminal operation in our in work with futures and promises. So, and what was this future in Java? Actually, it was a nice structure, quite nice. You probably all know this code. So we take an executor service, we submit some work inside, and we try to ask, is it done? Is it done? Click, is it done? Is it done? And as we are actually bored to be checking, is it done? We just get the result, and that's it. So the API is quite simplistic, but there is one small drawback in all these things. So we are quite close to theory, but we are not, because get and get timeout are blocking operations. Here, by these functions, get, we are actually breaking the law. So if we take a look at this diagram, so there is a main thread and a different thread that we submit the work there. We submit the work, and as we submit it, so we can continue our work as it is with zero downtime. We just continue our work in our thread, and this work is offloaded to be asynchronous. But, of course, we usually do get operation. As we do get operation, the main thread blocks, and we are waiting for thread 1 to finish its work. So all this time, when the results are ready, we are actually blocked. We're doing nothing. And what we want to somehow put the cat and do something useful in this main thread. So from the definitions, we don't have to wait or block. So how do we escape from this situation? So of course we do callbacks. Yes, we say, okay, I offload you the work, and then when you're ready, notify me somehow. Okay, let's imagine we have a kind of a construction which is done with Java 8 stuff, with suppliers and consumers. And this is actually doing one thing. So it takes an executor service, gets the result from a supplier, wraps it inside of a try-catch block, and on success it accepts it, or on fail it just, here I said accept, but we can write a log message or something like this. So, and let us try to do something useful. So we want to calculate Fibonacci's numbers, which can be a time-consuming operation. For my demos, I try not to use the internet because it's usually fails. So Fibonacci is quite, or even prime numbers. We can use prime numbers here. For next time, I'll write prime numbers are time-consuming operation, so it can be offloaded. And what we say, so we can asynchronously call Fibonacci, put it inside this executor, and print line. And if something goes wrong, we just, print stack trace. Okay, that looks pretty nice, With this small wrapper, we quite gracefully offload this work to another thread without even noticing it. But what if we want to change something? For example, we want to calculate prime numbers, like here. We want to calculate Fibonacci's numbers, and we want to make an intersection between this. I don't know, it's quite a weird idea, but for some mathematicians it may sound reasonable. I couldn't find reason personally, but it's a good example because it does not use internet. As you see, this code is not readable. It's not maintainable. It's not even debuggable, I would say. Because all the actual work happens here in these red lines, and it's ugly, I would say. Nobody writes like this, although we have all these opportunities to do this. And actually, the story is, did they try to do this somewhere else, all this approach? And of course, everybody remembers this Node.js stuff. How many of you have coded Node.js? in production. I mean, in real hardcore production. Lucky you. Because, they have introduced this non-blocking API with event-driven modal. And of course, well, the new for that time was that everything was made asynchronous based on callbacks. And there was so much cool about all this callback. We said, okay, this will, solve our problems. We don't need JavaScript itself is not a multi-threaded language, but we're still able to do this all asynchronous stuff very beautifully. But in reality, we came to this wonderful picture, callbacks everywhere. Yes, which led to some other picture which is called callback hell. Yes, in production it was undebuggable to work with this. And here I'm honored to cite Dr. Venkrap Subrahmanyam. So if you say callback to a JavaScript developer, he will start crying instantaneously. Yes, this was the message from his last session. Yeah, so in reality, it was not so much cool. And people started to think, okay, we need some other mechanism to fix this. And then came this promises library, Q library. So it was really a wonderful approach. So instead of doing this, inlining, I would say, function in function, calling back other function, the Q library actually allowed us to make a call, and then, with the construction of the word then, we could chain different events which are happening actually asynchronous, but we can chain them and gracefully handle exceptions and gracefully handle the final result. So all the things here are actually happening inside of a kind of a virtual container, which all the works happens inside of this construction of Q. And after we are done, we're just getting the value out of the container or do something else. So, but not only in JavaScript. So as you see, the future in Java 5, starting from Java 5, was actually a kind of a not full future. It was kind of a partial future which violated the law. And the guys from Google say, okay, we don't like it. We want to make it. A real future, as it should be by theory. So they have created this listenable future at this time, but it was complicated. It was really complicated. How many of you are using the production? Nobody. Sorry, maybe because of the lights. Nobody. Okay, you're kind of a lucky. Somebody of you have worked with Cassandra databases? Well, actually, there are futures from Guava. They say, okay, we have this contract of this operation, which can be, time-consuming. As it's time-consuming, we return you the future of this operation, but not just the future, but listenable future. So you can do more things with it. And to use it, it was hard. So we have to decorate our executor. We could add callbacks in quite a civilized way, but as I said, I tried to use it once in one project, and it was complicated. But it addressed a very, very good idea of the fact that we do not transform the value outside of this container. So actually everything happens inside of this virtual container, which handles all this work inside of a controlled environments of a future. And we can transform the values inside. So Guava gave us the opportunity to be more theoretically correct in using futures and promises. Then came another library. It's called JDeferred library. I think that Ray Tsang is one of the authors, and he is now on this conference. So you may talk to him. And there is a very nice article by Aleksandrov here, just happened now on this latest Java magazine, and it actually helped us a lot to work the same way as we did with the Q library. JD Furt, if you read in this article especially, is very good in the idea that we actually separate the futures from promises, which is not going to be able to do in pure Java. You may try, but there is one small drawback here, is that sometimes we are not allowed to use third-party libraries. There's quite a production situation, especially in banking environments. So for every library, you have to get a permission. And if we're not allowed, we have to do something else. And so the idea is how to achieve an asynchronicity in Java 8. And you will be surprised, maybe not surprised, because it's not a new material. So actually Java 8 is available since 2014. How many of you have actually used Java 8 in production? My God, how many of you use not only Java 8 JVM, but the features of Java 8, like streams? Well, fewer or less hands. So still in many companies, the migration of Java 8 happened to come just to migrate the same code to another JVM. This was a game changer, which was, in my opinion, comparable to lambdas and streams, but it was some kind of a little bit forgotten. So in Java 8, asynchronicity is done only by one single class. It's called the CompletableFuture. And it's available since actually 2014, March 2014, which is, and it's in the core library since Java 8. So what they did? So they have used the future interface, and they have added another interface, which is called completion stage. And CompletableFuture actually inherits from, extends two of this interface. As you know, in Java, we can extend multiple interfaces, not multiple classes. And they've added a lot of magic inside of this, on this completion stage. So from now on, we are able to do composition of elements, function resolutions, transform the values inside, chain the values inside, complete the futures, and do all these things synchronously and both asynchronously. To get to this class, we need to talk about some foundations. So the foundation, the main and first foundation, which makes us easy to use this class, are of course the lambdas and method references. So Java 8 actually had them, and the CompletableFuture, of course, benefits from them. So as you saw in the Guava example, it was very, very hard to write something reasonable for callbacks, because you have to write a lot of code, which is quite unmaintainable. It's really unmaintainable and undebuggable. So here you just use lambdas and method references. The second big foundation came actually from Java 7 as the fork join thread pool came available, and it became an amazing helper for asynchronous operations. Because why? So by the algorithm itself, it's care much for cache corruption. So what do you mean cache corruption? As you see, it's very good if one task operates on one single core. So, and we know as we use the data, the cache lines are filled with the data which is mostly used, and the cache hits are actually speed ups in this approach. But we don't have this unlimited resource, of course, and that's why we have to split our tasks to multiple cores. And fork join here with its work stealing algorithm and in its theory help us a lot to keep as much tasks in one processor the more time possible, and just right when the queue of operation is full and we have all the thread filled up with task, then it just steals back from the task from the task queue the last task, keeping the tasks like here which are closer to be executed in the same thread. That's why, caring about this cache corruption. So we are more likely to have cache lines, data cached inside our processor, which will be mostly used. So these two foundations. So in terms of how we use it, actually made it very, very easy to introduce CompletableFuture to our developers. So if we go back to CompletableFuture, so how can we create such a future? As we say, it's just a class. Since it's just a class, we can use a new operator. So we can create an empty container, I would say it like this, for some job to be done, just like create a new class. But there are much better ways to do this, which are actually supply async and run async. So there are static methods, and we just, as you see from the definition, we say the container, okay, so this is the work that has to be wrapped inside of a container and given to you, just supply async. Or with run async, this is the work that has to be done, please, as you run it, we don't care about the results, so just run async. By the way, let us try to do this. I have prepared some small code for you. I think that screen is so much big that you are able to see everything, yes? You have no reason to enlarge it. Or I'll do something like this. Is okay? Okay, so as we say, okay, we want to calculate prime numbers. Prime numbers is a time-consuming operation. And we want to do this in an asynchronous way. So we say CompletableFuture. Okay. Just give me a second. I will even do it like this. So okay, so get primes it's a very I've written the code here. So if we make a CompletableFuture of it, CompletableFuture, and as we say, we just supply some operation here, and we pass a method reference, which is, IDE is very great supporter here, and we say, after it's done, okay, please print it. Okay, system.out not dot, double dot. We need a method reference, print line. So we supply async. We say, okay, offload this somewhere else, calculate it, and after we're done, please show us the result. Well, what will happen? Okay, it's working, and actually nothing happens. What's wrong here? Why don't we have any result? Somebody has an idea? Exactly. So we have now just done our multi-threaded program without realizing that this is multi-threaded program. So, and if you say, for example, system out print line, and here we say, I don't know if I'm writing this correct, but this direction or the other direction? Okay. Krakow. You see, as it's asynchronous approach, we just run it, and we only receive here this hello Krakow, because the other thing is offloaded to different thread. And to realize, actually, we have to do some work. The work really happens. Is that we can do, for example, system.in.read something, just to prove that it's working. And you say it now works somewhere there, works. Okay, you see, after some times, the thread actually, as it's done, as it's calculated, we chained our events so that we just print them out. So our program is working, but we have just now done a multi-threaded programming without even realizing we're doing multi-threaded asynchronous programming. Looks pretty impressive, huh? So this is our approach. By the way, as you see, the power of CompletableFuture is so big that we actually can supply our own executors here. But for default, we use for a join pool. So as you say, for termination, we can actually complete this future or complete it exceptionally. That means that we're saying, OK, here we have a failure. We declare this as we have completed it exceptionally. But it can be completed only once. And as you probably saw, there are different ways to complete them as well. By chaining the method. So we start a new container, put some work inside of it, do some work, and we have a terminal operations like then accept that we consume the result or run something after the result is consumed. And by the way, remember this, so that the transformation has to be done inside of a container. This is nicely done by then apply function, for example. So, as you probably saw, we can now calculate this, and then we can chain somewhere else here. Like, for example, I think I have prepared initial get average. So we receive a list of operations, and we want to get an average of all this, prime numbers. And you see, we do all this transformation right inside of the container. The container does the value, the calculation itself does not leave the container. So that's kind of a very interesting result for mathematicians as well, like 9,000. I don't know why it's like this, but as you see, it's done completely asynchronously, and it complies the approach, the theory underneath. And as you see, it starts very, very beautifully. And if we dive deeper, we have a very big infrastructure here. So as you see, we can do smart transformations because as it's a class, we can return a completable future of a completable future of a completable future. That is absolutely possible and it's legal, but we don't want to do this. And that's why we have this then compose method and then compose async method, which help us to avoid this situation of completable future and completable future. It works just like a flat map. So it just unwraps it for us. It's very smart. We don't have to think about it. So if, for example, we have a synchronous operation of reading a file, and then we have an event like, for example, read the file, then process the file, and then print the result, we are absolutely okay to use the compose method. It will unwrap for us all these completable futures inside, and we are completely beautifully, asynchronously chained here. Or, for example, we want to combine some values. For example, some futures, we need a result of two futures. And we can use then combine method and then combine async method. So if we use, for example, to calculate prime numbers and Fibonacci's numbers, in terms of usual futures, we have to put this work in futures and then make two get operations, which is bad because gets are blocking. And with the construction of then combine, we don't need this. I will show you later in the demo. And of course, if we don't want a further processing, we can call, of course, method like accept both or run after both. So with two futures, as they are done, then accept both. Or accept some of them, accept either. That's an interesting situation. For example, you need, we just want a first available result. A good example here is a DNS. For example, we have several DNS servers, and we say, okay, all of you who knows this address, and the first returned address is actually something that we need. So it's we don't need other results from the other servers. But what happens to the second result, actually? The second result, the idea is that this future actually never completes. And it may be hanging around because there are, by the constructions of, not construction, but the approach of future, several other futures can be, dependent on your future. So by this operation, like accept either or run after either, you just handle with care. You can also get the number of dependents to see. So of course, we can apply to either operation. So as they are done, we can apply some transformation. Or we can have a more generic method, like called all of the futures. So we can wait for all of the futures to finish, or any of the futures to finish, just like in this DNS approach and the DNS example. But please have a look at their results. So all of is void, because here we cannot predict what actually what are the other futures made of. We can supply futures of string, integer, or another class. Here we cannot predict what will be the first available, or all of the first. It's not possible. For any, we have an escape of object, as you see. So it should be an object, but then it will be kind of uncertain what will come next. So here we lose the type information. That's why I personally never use these methods inside of my production. And as we were talking about the exception on the previous session of Dr. Venkat Subramanian, you see exceptions in these approaches are handled like normal operation. That's not a stop of the world. And all of the approach of this asynchronous completable futures are the idea that exception can happen. And we are able to gracefully handle this exception and make it part of all of our process. So first of all, as you see, we can exceptionally finish our future, or we can handle it with a handle function, which actually accepts by function, which is kind of beautiful, because here you have this lambda with two values. First one is the value which is produced, and the next one is exception. So if everything is okay, we just continue, or if we have an exception, we just do something else. So we can, put it inside of the chain and gracefully handle, because the exception is propagated through all of the chain. And here, this is a normal result. So if we go back to all this, to this function about reading files, you see the code itself becomes very, very beautiful. So we supply it asynchronously, we receive a future, we compose it with our future as it is, we print the results, and if something goes wrong, we can handle it gracefully. And as you probably noticed, so unlike the future, the API of the class is really big. Yes, although it mostly fits, so we have methods that have synchronous and asynchronous versions of it, but it most fits to this pattern. But there are almost 60 methods inside it. That's why this class is called one of the scariest in Java 8. There are many friends of mine say, why don't you use completable futures? They say, because we don't understand all these method names. Yes, it's very hard to use. But still, if you get used to them, it will come very naturally for you. I personally believe that this is one of the game changers in Java itself in decades. So, completable futures are very nice if you start to think about these chains or flows of events and events in tasks themselves. So, not every problem is okay, but if you are able to think in flows, events, and tasks, futures, completable future construction itself is something for you. But here we have some bad heredity, and of course is the get method. Get method is blocking. So because we actually inherit from completable future, and we have to live with it. But this get method is actually both good and bad, because with get method, you are able to do synchronous calculations. So for example, if you are designing an API and you declare by saying that this result is wrapped in a completable future, you somehow declare to your customer that, okay, this operation may take time. It's a long-lasting operation. And the client itself can decide, okay, is this a long-lasting operation? I can change some event, or if I want to make it synchronous, I just make get the function, get the result. And as you see, because there are streams, they have created also a join operation. This join operation is very interesting. It's also a get operation, but this get operation does not throw checked exception. And it's very beautiful. I've made a small demo for you. How can we use this? As we see, we are able to do some asynchronous jobs, some parallel asynchronous jobs. Let's imagine the following situation. We have to send several emails. These emails can be sent absolutely asynchronously and in parallel. These operations are not dependent from each other. So, and how can we? How do we usually do this? So we do this with parallel streams because they are just very easy to use. But let us. So I'll show you the task itself. The task itself is currently very, very easy. So we just sleep for 1 minute, but maybe here we're sending an email. Since we don't have internet, we will imagine this. We do parallel task, but we want to make it a little bit different. We say, okay, so sending a task, we will wrap it in a completable future and just throw away somewhere asynchronously. And then we receive back the results. Why do we want to do this? Because in parallel streams, we are not able, by means of the construction of parallel streams, to say which executor should be used. And in parallel streams, we only have this fork join pool available to us. Here in CompletableFuture, as you saw the construction, we can submit other executors, and we want to benefit from this. And as you will notice, which is interesting here, if we run the same stuff here, just give me some more time. As we construct here by parallel streams, you will see that we have a fork join pool common worker, so we're using fork join. But all the sending of an emails will take, each of the tasks lasts 1 second, but it takes about 2 seconds to send all of the messages. If we do the same thing here with CompletableFuture and submitting it to other executor, which now I think is not a fork join executor, but just a usual fixed thread executor, we will do the same task only in 1 second. You see, this availability of executors to be submitted to CompletableFuture makes us a very good job, because the CompletableFuture itself can now benefit from other thread pools. And we are okay and we have really 1 second benefit here, which is observable. So when this join operation is kind of a get, which is not blocking operation, it's done mainly for working with streams, because in streams we don't have the possibility to work as check exception. So you can also obtrude a value, which is to see what's happening inside, but never do this. So, but have in mind, a good example for this, which we actually use in our project, is that we, as an enterprise, we want to calculate something in a synchronous way and send it back to the client. And unfortunately, before Java EE 7, we had to use these get operations because we didn't have any construction for this. We have to do asynchronous stuff to a certain point. After Java EE, it looked like this. So all of our main thread actually was blocked every time, while 2 threads were calculating the values. But in E7, we had the possibility to do an asynchronous response. We had an infrastructure to do everything asynchronously. So we calculate all our stuff here, we apply the results, we apply the results directly to this asynchronous response. So we received an opportunity to make a real chain of asynchronous events, even on the server. So that's a good example for this. So as you see, the primes, as the values are calculated, we are not blocked in this part. And not only on the server itself, in JavaScript, we have received a possibility even on the server to get this, because with the new Rx function, we receive as a result a completion stage, not just a future. So we are able to do this truly asynchronous on both on server and client. But still believe get is evil. I mean, if you are designing your API, try not to use get if you are trying to make it asynchronous. And as you know, Java 8 arrives in July 17, or not exactly July 17, or we don't know. Yes, there is a JEP which actually extends the work, and it gives you a possibility to make some better work with CompletableFuture. So it's not only tied to Java 8. And as you see, there is some strange work. If you supply asynchronously, work, we can complete it with a default value and make our get method not blocking. And we say, okay, while this value is calculated, please submit us, always return another value, which is the default value, for example. If we call get. But this makes the program a little bit unpredictable. So we can complete the future, and the good part here is that we have more possibilities to work with timers and schedules. By the way, the first talk about CompletableFuture was done by your citizen Tomasz Nurkiewicz, I think. Amazing guy. And there he introduced this unblocking timers and schedulers with some tricks. A very nice idea. But here you can do this even more beautiful. So we have timeouts built inside of the completable futures. So, and you can complete it both with by function. So if the price is calculated like in this example, please do something. If not, sorry, we cannot return. So we are tied to timers here. Or we have this complete on timeout. We can either have a default value, or in 1 second, for example, in one amount of time. Or we can, if it's not calculated in this period of defined time, then return something default. It's an option, but still there is, my personal approach is that there are several uncertainties about undefined behavior. So this undefined behavior is dependent now on time, and it's very hard to see if the program is actually returning and responding correctly. But at the end, I want to say a few words about Reactive, yes. Dr. Venkat Subramanian gave a very good explanation about Reactive, but still I'll have my small approach. So what is Reactive? As you say, it was the new cloud. So if you program reactively, you have all these benefits, yes, which are written here. Yes, but until the serverless came out. So now if you use serverless, you will receive more benefits. But still, it's not something new. As you say, it's observable pattern, so the keyword is asynchronous. And actually, this CompletableFuture is quite near to this pattern, as we say. If we read this wonderful manifesto, now everything has manifestos, and Reactive has its own manifesto, of course. And of course, we take a look at this wonderful picture, which is shown on every conference worldwide. We still see that CompletableFuture is quite nicely fit in this idea of responsive elastic, as we say. We work with the resources. We use multithreading underneath without even realizing we have the multithreading. And it's very resilient, so we keep the exceptions as a part of the flow, and they're handled gracefully now in this case. The only thing is hidden from us, this message-driven idea. So this message-driven idea that, okay, I'm here, I have finished my task, I now signal you to continue by the chain to do the same stuff, it's hidden from us. So we don't have this message-driven available. But still, as you see, Reactive is good for CPU usage, for cache usage, and so on and so on. And even if I've created, as an example, API, and see that by using only completable futures, by these gaps that we don't have to count without this blocking, we see that it could serve more responses today. So the blue graphs is actually the result, but it's only by introducing this non-blocking approach. So it looks really nice, quite nicely fits to reactive patterns. And what's good about CompletableFuture is that it comes out of the box. You know, you don't have to think to use different libraries and to, care for them much, because if it comes with a JDK, then it is tested. What is beautiful about something that comes from the JDK, it is tested. It works good. It works proven. So Java 8 is one of these things, but handle this care. And I say once again, mind the gap. So in synchronous application, you may have it. In asynchronous, you can, do it without it. And that's all from my side. So I say dziękuję bardzo.